So, we have already defined Riemann's integral, its basic properties, basic associated ideas with it. Now, it is time that we put it through some litmus test, that is it really the integral as we know it from Newton or Newton or Leibniz, that it has some properties like the integral of the addition of two functions is same as the addition of the integral of the two component function, two individual functions. So, that is a litmus test, that if all these rules that we have studied for integration in the sense of Newton can be applied now, can be also showed for that of Riemann, then the Riemann integral passes the litmus test and then it becomes some sort of acceptable integral. So, we will now write, if a function is Riemann integrable, we will write that f is in RAB. So, you can have your own sign invented for this set, that just to mean. So, whenever I am talking about a Riemann integrable function, I am assuming a bounded function. I am not telling that, oh, it is something I do not know, unbounded, just it, then I am trying to prove that f is bounded. Obviously, you can do that, but that is not what we really do in. So, this simply means f must be bounded, BDD for short. F is bounded and Riemann integrable. So, this is the collection of bounded functions which are Riemann integrable. Now, if f and g, both are in RAB, so what is the relation between these two numerical quantities? Now, here integration is in the Riemann sense. Does this relationship hold true? Yeah, your mind or our mind might be tempted to think that, oh, it definitely does. Actually, it does, but you need to provide a solid backup, or rather a proof to the thing that this thing really works. So, how would you go about doing so? So, you take a partition P. So, P is an element of P, where P is the set of all partitions, as we had discussed noted in the last class. Now, let Mi be the inf of f plus g, okay, over when x varies over the interval, or xi and xi minus 1. And let Mi dash and Mi double dash, this is the inf of f over the same interval, and Mi double dash is inf over g for the same interval. Now, there must be it might be very easy, tempting to think that Mi is equal to Mi dash plus Mi double dash, but this is grossly incorrect. I would rather tell you to go back home and try out this very simple exercise, that if you have you are taking the infimum of a function fx or f plus g of x over x belonging to some set A, does not matter what is it, set A, then this is bigger than the inf of f plus inf of g x element of A. You can write f x g x, does not matter. So, this is actually the formula. So, this is something you should prove. So, what I actually have here is that m of I is bigger than m of I dash plus m of I double dash. So, let us look at the supremum. So, I can write mi, capital Mi as a supremum of f plus g. Maybe I should write f plus gx if you want to be more, you want to look more precise, and x is lying between in the interval xi minus 1. Then I will say mi dash and mi dash are the supremum over the same interval. This is for f and this is for g. Do not say that the sum of these two is equal to this is grossly incorrect again. So, again go back home and look into, just try to prove this simple formula where A is a subset in R. Okay. So, the sup of f plus g is less than sup of f plus sup of g. So, what I have here is another thing. So, what I now can write from here, that m of I is less than equal to capital M of I dash plus capital M of I double dash. So, what does this give me? If you are very clever, if you are just clever enough to see through it, you will immediately realize that these things appear, this appears with the lower sum of g, this with the lower sum of f, and this with the lower sum of f plus g. So, what I have in effect proved is LF P plus L GP is less than equal to L of f plus g p. While for the upper case it is the reverse. Upper case you will prove that u of f plus g p for any given partition p is less than u of f p plus u of g p. This is a key idea, because without this you can't do much, right. So, what you have actually proved? You have proved that L F P plus L G P is less than equal to L F plus G P. This inequality becomes handy later on. F plus G P, which is less than equal to U F P plus U G P. So, we are just combining these two. So, this is what you have at this moment. Now, f and g are assumed to be integrable, right? That is what we have assumed, f and g are they are Riemann integrable. So, since f and g are in R, are in RAB, what would it imply? It would imply, see, now you are using the Darboux format to do everything, because we have told at the end yesterday that Darboux's approach and Riemann's thing are essentially the same thing. So, they give the same value for every, the class of functions which they integrate are the same. So, So, now Darboux approach is easier to handle, so we are using the Darboux approach. So, since f and g are in RAB, so what I have? So, there exists partitions. So, for any given epsilon greater than 0, there exists partitions P dash and P double dash such that U f P dash minus L f P dash is strictly less than epsilon by 2 and U G P double dash minus L G P double dash strictly less than epsilon by 2. That is what the idea is. Now, consider a P. Let P be the union of P dash union P double dash. Now, I leave you to do this formidable exercise, that then what would happen? Then UFP minus LFP is less than this and UGP minus LGP is less than this and hence less than this. So, what you can prove is UFP plus UGP, this minus LFP, basically now adding up, plus LGP, this thing is strictly less than epsilon. This is what you can finally prove. And consequently, what do you prove? So, you have already proved that this is bigger than this and minus of this is bigger than this. So, what you have finally proved? You have proved that U of, because here this part is bigger than this part. So, this minus this is less than epsilon. So, if you take this thing to this part and add it with epsilon, then you can apply that this plus this is less than this. So, ultimately you will get U of f plus Gp, please check the calculation, minus LF plus Gp is strictly less than epsilon. So, what you have demonstrated, that if f and g is in RAB, it implies that f plus g is in RAB. So, now this integral now becomes meaningful. So, that is why I put a question mark here. Now, this integral becomes meaningful. Now, the question is whether this is equal to this, these two things. That is the first step. So, this shows, this actually is showing that f plus g is in RAB. So, it is Riemann integrable function between RAB. Okay. So, that part being over, we will now transfer ourselves to this part, so that you can see the working that side. So, now let us look at this. Now, we will use this thing that we have proved. Now, what we have proved is U of Fp plus U of Gp, right, is less than this, is less than L of Fp plus L of Gp plus an epsilon. That is what we have proved, because once we have wanted to prove that thing. So, this information is there. But this again, as you have proved here, so what do you have from here? What do you have? You have the following. You have U of Fp plus U of Gp Now I am applying this fact on this. So, it will give me L of f plus g p, okay. So, the integral is the supremum of the lower bound, right, plus epsilon. So, what is this? This is nothing but integral of, this is less than integral of a to b f plus g x dx plus epsilon. And what do I have here? Each one of these are bigger than their respective integral. So, this part is bigger than integral of this, because this is the infimum of this over all the partitions, plus this part is integral a to b You agree to this? So, this is what you have proved, right. So, what you have proved, integral a b f x dx plus integral a b g x dx is less than equal to integral a to b f plus g x f plus g x f plus g x dx plus epsilon. That is what you have proved. Okay. Now this part been done. So, you have this equation now. So, this equation is there. So, epsilon is there, you have proved this equation. I prove this inequality. Now, I will prove something else which will, so I am just removing this part and let me just see what we can do with the remaining part. So, you will use the same sort of explanation. So, from here I can write using this fact from this equation, please note u of f plus g p, which is less than equal to this, and hence it is less than equal to L of f p plus L of g p plus epsilon. So, u of f plus g p minus epsilon is less than equal to L of f p plus L of g p, and you know that u g p is bigger than the integral f plus g, because f plus g is already proved to be Riemann integral. So, a to b f plus g x dx minus epsilon is less than equal to, each of these are less than their individual integrals. This is less than the integral a to b, because the integral is the inf of this. So, the integral is the sup of this. So, the integral is essentially, so the upper bound. So, similarly for this one, by the very definition of the integral, you have this. So, what are you getting? So, this plus this is this plus epsilon, and this minus epsilon is also less than this. So, this plus this is less than f plus g plus epsilon, and f plus g minus epsilon is less than this. So, combining these two equations, maybe I can rub this part now. So, I will put some numbers there. So, maybe a and b. So, I will put this equation as a inequality and this inequality as b. So, combining a and b, we have integral a to b fx dx plus integral a to b gx dx minus integral a to b f plus gx dx is lying between epsilon and minus epsilon. So, if I take epsilon to be 0, if I make this is true for any epsilon, I can make epsilon 0 from both sides. So, by the sandwich theorem which you know about limits, if the limits are 0 from both sides, then the limit of the quantity inside must be 0, but this quantity is free of epsilon. So, this the limit is the same as this quantity. So, or if you want to be more precise, this simply means integral a to b fx dx plus integral a to b gx dx minus integral a to b f plus g x dx, this is less than epsilon. So, this since this is less than any epsilon greater than 0, it does not matter whatever be the epsilon, the only non-negative number which can be made as small as I like is 0. So, means this thing, this absolute value of this thing is 0. So, any quantity whose absolute value is 0 is 0. So, it showing that integral a to b fx dx plus integral a to b gx dx is equal to integral a to b fx f plus g x dx. So, you see it needs a lot of work to really go ahead and prove this calculus, this important rule for integrals which we knew earlier, but now we have done it for Riemann and you see that it actually works. So, Riemann's integral passes the first test. Now, there is something else which we want to the proof. There is no much time that to spend on proofs, but this result that I want to now write down. So, let me take a point C which is lying in AB, say maybe a midpoint something like that. Of course, I can take C is equal to A and B, but they will become degenerate points and there will be unnecessary complexities which you do not require. If C is in AB and then F element of RAB, F is Riemann integrable if and only if F is element of AC and F is element of RAC and RCB, means F is Riemann integrable over AB if and only if I take any point between A and B, F must be Riemann integrable over each of the separate components, separate parts. So, if I have A, C, B, F is Riemann integrable over the whole if F is Riemann integrable over this part and each of these individual part, and if F is Riemann integrable over each of this individual part, then F must be Riemann integrable over the whole. So, it needs certain time to prove this. I would leave it to you to really work this out, and in that case you can actually show that integral from A to B f x dx is equal to integral from A to C f x dx plus integral from B to C f x C to B f x dx. Now, in our analysis we have always assumed that the integral, when we are evaluating the integral A to B, this integral from A to B is valid when A is bigger than B. That has been the approach. But again, just like the way we did for the Newtonian case, we can make a definition. The definition is the following. The definition is that if A is not bigger than B, that is B is not bigger than A is bigger than B. So, B to A, what does it mean? How do I define it? This is defined as minus A to B fx dx. So, kindly take this as a definition. This is true when A is when B is strictly bigger than A, then if I write the integral from a bigger value to a smaller value, this is negative of the integral from A to B. It is same as the area explanation that I have given you, the same idea, but now just we have picked that definition up and put it in here. So, once you do that, once you have that definition in, then this C being a requirement to be inside A and B is no longer valid. You can just put C anywhere and get the result. And of course, you can show for Riemann integration theory that if I multiply C with a function any number, we construct a function Cf, which is defined as so C of fx is Cf of x is nothing but C times f of x. So, in this case, so the integral of Cf is C times integral of f. I am just writing very shorthand things, but these are very common things that you can learn up yourself from any books or even the net. Important result that is there, for which we do not need any extra styling or extra information, but this is an important result which we would not prove because the proof would take in a lot of time, but we are going to state this, and because this idea would be important when we start to have a look at the mean value theorem for Riemann integrals and their applications. So, you can look into the proof. These are the things. Let me tell you, I am going to give you notes. I will start giving it out maybe from tomorrow. I will give my TS some notes of the first chapters. But if I start giving, I am trying to build up the notes, but the course duration is so short that such a huge thing cannot be covered. I mean, I would not have time to write down the whole notes in every detail possible way. So, wherever some proofs are not being given in the class, the proofs would be given. For example, these ideas are from Spivak, but here proof styles, but here I have done more detailing work which is not given in the book. So, for the proof we had just done. So, what I am trying to say is that I will give my TS whichever proofs are not given, whichever ideas are not introduced in the class in detail, those things will come in the notes. So, they would not be coming so rapidly, but they would be in the notes, they would be there for a long time, and I am sure you can learn things even after the examination. It is not that exam is the end of each and everything. So, here I will not give the proof because the proof would be not so easy to comprehend immediately, but I will get this proof and the proof of the other one done through, I will write these proofs up and they will be scanned and put up, and then you can really look into it very carefully and try to understand them, because if I explain them, I have to explain them fast because of time constraints, and then you lose the idea. The idea is this, here is the important result, and that is, with this we wrap up today's discussion. So, if F is element of RAB, okay, and X is a number between A and B. So, and say X is any number between A, B, define f of x as integral a to x fx dx, then f is continuous on AB. of course, using this and this fact, you can prove that integral a to a is nothing but 0. So, f of a is 0 here and then it begins. So, this is very important because function f need not be continuous, but the what you can call as the antiderivative if you want to call it, this one is actually a continuous function. This is something very important to keep in mind. The proof will be given in actually in the notes. So, with this we end the class today. In tomorrow's class we are first going to talk about the mean value theorem and its application, and then we see that how the integral of Riemann can be, that is very recent development in the 60s, I would say, very 30-40 years, not much. So, we are trying to also push in some recent research ideas into the class, so that you get a feel of how mathematics develops, how mathematics progresses, because many of you have the idea that mathematics when I learned it at the first year engineering level or first year level in any professional course, mathematics ends there, goodbye, you just solve problems. So, mathematicians are people who are solving problems from calculus books or some books of linear algebra or some complex analysis books. This is what one thinks about mathematics, this is what one feels that mathematics is, that is the general idea about mathematics in our community. But I want to bring in this lecture because I am evolving the course rather than following strictly to what I initially thought, because I want to evolve it, because I want to show that mathematics is not a dead subject, or calculus or integration, all these ideas are not just dead which has stopped somewhere. People are still evolving them, and that is very important, that this evolution. So, here I am trying to show you how this, even Riemann's idea which was some 100 plus years ago, how that was evolved. That is very important, this evolution of ideas, that mathematics is not something which has it has ended once you have given the first year calculus lectures, you can pack up. And so, mathematicians are usually a useless bunch of people who are just given money to teach calculus. That is the general idea, and many people have actually told me this, but that is really not. Mathematicians are there to dream and bring mathematics to a level which was unseen earlier. So, that is what I really want to show you. So, that is why I am putting in this lecture, which is really not a part of a traditional calculus course. If I write a calculus book sometimes in my life, I do not know whether I will ever do it, but I would definitely put a chapter on the Henstock-Kurzweil integral, which is also called the generalized Riemann integral. So, which would be part of the section on the 5th week of your studies. Thank you very much.